All right, in this video, we're going to look at two different reactions that we can use to make ethers. The first reaction is called Williamson ether synthesis. In Williamson ether synthesis, we start with an alcohol, and the reagents we use are sodium hydride and then an alkyl halide. And the product will be the ether that includes the R group that we started with in the alcohol, plus the R group from the alkyl halide, both coming off of the oxygen atom. Now, the mechanism is pretty straightforward. So we learned last chapter that we could use sodium hydride to deprotonate an alcohol. And so that's what happens in the first step. So we have the sodium hydride, right? We have the proton transfer, where the hydride ion steals the hydrogen from the alcohol. That bond becomes a lone pair on the oxygen, right? That makes an alkoxide ion, right? And so this RO minus, if you remember from last semester, this is both a strong base and a strong nucleophile. And so if it acts as a nucleophile, we'll get an SN2 reaction where the alkoxide ion replaces the leaving group from the alkyl halide. Now, this second step is an SN2 reaction. And so if you remember, when we have something that's both a strong base and a strong nucleophile, we can get both SN2 and E2 reactions occurring. And so if the alkyl halide is primary or methyl, then the SN2 mechanism will dominate. But if we have a secondary or a tertiary alkyl halide, we're going to get elimination primarily instead of substitution. So this Williamson ether synthesis only works well when the alkyl halide is either primary or methyl, right? And then there are no restrictions on the alcohol. Okay, so as an example, let's consider how we might make methyl tert butyl ether, or MTBE, using Williamson ether synthesis. So in the Williamson ether synthesis, I need an alcohol and an alkyl halide, right? And so we can imagine two different routes, right? I could use the alcohol with the tert butyl group, or I could use the alcohol with the methyl group. Right? If I choose for the alcohol to have the tert butyl group, then the alkyl halide is going to contribute the methyl group. Right? Alternatively, if the alcohol has the methyl group, then the alkyl halide has to have the tert butyl group. Right? In between these two different approaches, this first one should work fine. Right? We said on the last slide that because that second step is an SN2 process, we need the alcohol to be either methyl or primary. And in this case, the alkyl halide is methyl. So this should be a viable way to produce MTBE through Williamson ether synthesis. Right? If we imagine the other approach, where we start with the methyl group coming from the alcohol, then that tert butyl group would have to come from the alkyl halide, right? But this is a tertiary alkyl halide, right? And so that's no good for an SN2 reaction. Instead, right, when we make the alkoxide ion from this, right, by deprotonating it with sodium hydride, right, that is going to be both a strong base and a strong nucleophile. Because this is tertiary, we're going to get elimination and not substitution, so we're not going to get the product that we desire. Okay, so we just talked about Williamson ether synthesis. The second reaction that we're going to learn to make ethers is called alkoxymercuration demercuration, right? And hopefully that sounds familiar to a reaction that we learned last semester, right? Last semester we learned oxymercuration demercuration, and this is an example of the reaction that we learned last semester. This is oxymercuration demercuration, right? So when we use this mercury acetate compound with water and then hit it with sodium borohydride, we add an OH in using Markovnikov regioselectivity, right? And we don't get a carbocation rearrangement, right? So let's see on the next slide what alkoxymercuration demercuration. So it's the same basic process, right? And the reagents are almost identical. In this case, though, instead of using the mercury acetate compound and water, we're going to use the mercury acetate compound and an alcohol. And when we do that, we're going to get Markovnikov addition again, but instead of adding an OH, we're going to add the OR from the alcohol. All right, so let's take a look at examples of the two reactions that we just learned. So in this first example, we want to produce this ether using Williamson ether synthesis. So in this reaction, I'm going to start with an alcohol, and then I'm going to react it with sodium hydride and then an alkyl halide. And so one of the R groups is going to be provided by the alcohol, and the other R group is going to be provided by the alkyl halide. And so we need to make the choice on which one is going to be which. Sometimes it matters, sometimes it may not. So let's first imagine getting the R group, this R group from the alcohol, and then we can try and get this R group from the alkyl halide. So my starting material would be this alcohol, and then I'd need to first react it with sodium hydride, and then I'd need to react it with an alkyl halide. All right. Now, does anybody see a potential problem with this? Well, I think the problem is going to be that this is a secondary alkyl halide. And so when I deprotonate this with the sodium hydride, right, instead of getting substitution, I'm going to get elimination. And so that is not going to give me the ether that I want, right? Instead, if I get the alcohol from this, then I'll react that with NaH, and the alkyl halide would be that, right? This now is a primary alkyl halide, and so that will prefer substitution, and so that will give me my desired product. All right, and so that is the last slide for this video. Nope, I lied. There's one more slide. All right, so in the last example, we looked at Williamson ether synthesis. Now we're going to look at alkoxymercuration demercuration. And the ether that we want to make in this case is isopropyl propyl ether. So there's the propyl, there's the isopropyl, and then we have the added caveat that I can only use propene as my source of carbon atoms. So I can use any other reagents I want, but they can't provide carbon atoms. So propene is, of course, that. Now, the good news, right, 1, 2, 3 carbon atoms, and then each of my R groups has 3 carbon atoms, so that should be fine. And if you remember in alkoxymercuration demercuration, I'm going to add an alcohol to an alkene. And I'm going to do so using Markovnikov regioselectivity. So if I imagine adding an alcohol to this alkene, right, because it's going to be Markovnikov addition, it's going to add it here, right? And so that should give me my isopropyl group, right? And so then the alcohol that I need to react with this alkene is going to be one where the OH is on the end. So it's going to be 1 propanol. Right? So because this is my only source of carbon atoms, I need to turn this into 1 propanol. And so to do that, I can use hydroboration oxidation. That gives me anti-Markovnikov addition. And so I'll put the OH on the end rather than on the more substituted carbon. So for hydroboration oxidation, I'm going to use BH3 and THF. And second step, hydrogen peroxide and sodium hydroxide. Right, this is a reaction that we learned last semester. Right, that will give me the 1 propanol that I need. Right, and so then to make this ether, I can start with my propene, and then to get the alkoxymercuration demercuration, right? So the only difference between this and the reaction we learned last semester is rather than using water, I'm going to use the alcohol that I want. And then in the second step, NaBH4. So in these 2 steps, take my 1 propene, do hydroboration oxidation to give me the alcohol that I need. Then I'll start with my alkene, and I'll get Markovnikov addition of this alcohol into my alkene. And so this will give me the desired ether.